Hello and welcome back to Calculus 3, section 13.6, center of mass. We are going to discuss the way to find the center of mass in 1D, 2D, and 3D. And we're going to do so by calculating the mass of the object and calculating the moment for the spin around the point or axis. Now, for these moments, or mass first mass. So for mass calculations, we have to first consider that the objects might not be uniform. So if they are non-uniform objects, that means that the distribution of mass is not uniform, and we have and we need the total mass for this calculation. So we have to use integral. So generally, when you put something on a scale and says it's 3 kilograms, it's 3 kilograms, right? But we also have to make sure that it's distributed the way that will be that the mass is distributed. I lost my words now. That is distributed on both sides. There we go. It's distributed on both sides of the central mass, or if it's in a plane equally in a disc-like area, or for the 3D spherically, right around the center of mass, and then so it doesn't get flipped with when you try to turn it or flip it or whatever. So let's start first with a long rod, which is going to have a center of mass somewhere. Now, the mass for this one is given from A to B, and then we have rho x dx. Rho x is the density function. So rho of x is density function. And clearly, when something is more dense, then it's heavier, and when something is less dense, it's lighter. So we can find the density. We can find the mass of the object by integrating density. And again, because density doesn't have to be uniform, we will use the integral to compute that. And then we are going to say that somewhere on this 0 to, let's say, well, now we're using A and B. So from A to B, there is some location X, right, somewhere where this center of mass is going to be. Now, that is going to be what we call a fixed point, and we are going to have a moment around this fixed point that will try to rotate this bar, if it's not perfectly balanced, one way or the other way. And it's going to be called capital M. So now we have a calculation for this capital M, which will take the location X, right, multiplied with the density function, dx from A to B, and that one will calculate the moment. So now the x bar is moment divided by mass, and that's the location to balance it. So these three formulas together are the ones that calculate one-dimensional, right? So if you're just balancing the length. So as I said, as I stack these four markers, right, head to tail, as I stack these four markers, I still understand this is a three-dimensional object, but the length of these markers really surpasses the width, so I don't have to worry about three-dimensionality because it's kind of uniform in that sense. You can see that we can balance this one, right, on the middle, because we expect the mass on the left and the mass on the right to be the same. Please don't confuse mass with weight. Okay, weight is a force, which is mass times gravity. And the mass is the part of the weight. So it's not the weight, it's part of the weight. What is mass? Mass is a physical quantification of physical existence. Okay, that's what it is. So yes, the amount of stuff. So the mass is calculated simply through the integral of the density over there. And you know, when you see the calculation now, if you kind of pay attention, mathematically this doesn't happen because this is clearly, you know, in the realm of average. But if you are dividing the integral x rho x with the integral of rho x, and you kind of cancel everything, you are left with x right in that division. So technically that's what happened. But you can't do these things. These integrals and things don't cancel. So you actually have to compute everything. But you see that dimensionally it makes sense. Right? Dimensionally it makes sense. So now, let's take an example for 1D and then move to 2D. Now when you are on 2D, it's going to be already fun. Alright, so this thing is taking forever, so I'm just going to make up a problem. So say that you have a density function that is x squared plus 3x. So it's x squared plus 3x, and all of that is on 1 to, let's say 1 to 3. This is all you need. Right? You have a density distribution, and now with this density distribution you go and you just plug in everything in the formula. So the mass is going to be integral 1 to 3 of x squared plus 3x in parentheses dx, and when you compute this you get x cubed over 3 plus 3x squared over 2 from 1 to 3, and that's going to give you a number. So that's 27, that's a 9 plus 27 over 2 minus 1/3 and then minus 3/2. So that's 9. 24 over 2 is 12 minus 1/3. That's 21, so 20 and 2/3. That's a 62 over 3. Because we'll be canceling. Now the moment calculation is going to be integral 1 to 3 x times x squared plus 3x dx. And now we distribute the x. So this is all calc 1, obviously, calculations. 3x squared dx. It's x to the 4 over 4 plus this is just x cubed from 1 to 3. Now when you plug in, this is 81 over 4 plus 27 minus 1/4 and then minus 1. So 81 minus 1/4 is 80 over 4 is 20. Plus 26, right? So 46 for everything. And the last thing we have to do is to find the x bar, which is right the location where you get to average. Now, should we all first use some common sense and realize that the answer must be between 1 and 3?
Should we?
Yeah.
Should we use common sense?
Look at this. You have the integral 1 to 3, right? Can the center of mass be outside of this? The answer is hell no. So your answer better be somewhere between 1 and 3. And you know immediately that the problem is wrong if it's not. So we have the moment divided by 62 over 3. That's 120, 138 divided by 62. And what do we get for this? We get 2 point something. What? 226. Okay, so we'll call it 23. All right, that's that. So now our number is between 1 and 3. It makes sense. Also, it makes sense to be closer to 3 than to 1. Because remember, your quadratic function looks like this, right? And if the quadratic function looks like that, and you have your 1 to 3, you see that it's denser on a side where 3 is than side where 1 is. Does that make sense as well? So if there's more density on this side, there is more mass on that side, which moves the central mass towards the heavier side, right? Just think of a seesaw. If you have an unequal seesaw, this is where you would put a fat kid, and this is where you will put those skinny kids, right? And then it's balanced. This side, more dense. No one? All right, fine. As a kid, I was always on the dense side, so yeah. Now we're going to move to the realm of 2D. So 2D. You have some shape, and you are looking for location, and now that location is x bar, y bar, which is the center of mass. So that when you take that two-dimensional shape and rest on the tip of your finger at that point, that shape will not wobble, will not spin to fall, right? It will just stay perfectly leveled, perfectly flat. So that is the goal for two-dimensional center of mass. What are we looking for? Again, we are looking for the mass of the object, which will now have a two-dimensional density function as the input. And then we are going to find the moments on x-axis and moments of y-axis, which will provide us with a, once we divide each one of those by mass, provide us with a location for the perfect balance. So we start with the integral for a mass. It's going to be a double integral over region R of a density function that is xy dA. Note that this is the most general way to write the double integral. This could be rectangular integral, could be general integral, could be polar coordinates. If it's polar coordinates, that dA is r dr d theta, right? So for the mass, we are going to take the density function, which is distribution of density across this 2D surface, and then we are going to integrate it over its shape. Now the shape of the 2D surface is going to be the shape of the object, and since it's two-dimensional, we have something to worry about. So if it's a disk or half a disk or something like that, clearly we are using polar coordinates. If it's a rectangle, a square, and triangles and all of these kind of things, we will be using our rectangular coordinates. Or if there are two functions that are intersected, right, creating something, sure, still use the same thing. So that's that part. And then we have the moments. Remember that you have a moment in terms of the x and the moment in terms of the y. When you balance the object, right, the 2D object, you can use any sturdy piece of cardboard or whatever, and you just use two fingers, right, that will represent, let's say, x-axis. So if the two fingers that you put apart are representing the x-axis and you rest your cardboard piece on top, well, the y So that creates the rotation in y, right? Because it tries to dip the y-axis way. So if x is going towards you or away from you, then y goes sideways, and you see that it's wobble in y, right? So that helps with your equations. Your mx is going to be a double integral of y rho xy dA over the surface R, and your moment in y is going to be x rho xy dA. And now we need to find those locations. So to find the location on x, the x bar, we are going to take the mx and divide by the mass. And to find the y bar, we are going to take my and divide by mass. So now you have these 5 equations here that create the two-dimensional case. Now I'm trying to find if they have this in a book somewhere, but they don't. Oh wait, guys, I swapped. This is my, x is my, and this is mx. There we go. Much better. So your goal is to find the x bar and y bar, and those two will be numbers. Now, again, common sense, that the coordinates of that point better be within the bounds of your object, right? Imagine if your object did not contain 10, 1 at all in its, right? It's, let's say, 4 by 4 square centered at the origin, and your calculation tells you that you will balance that if you put the 10, 1 somewhere. So again, there is some way to check all of these, because tends to be a lot of calculations here. You have a lot of integrals. This is another one of those sections that are very good for killing time in carpal tunnels.
What if it's a donut?
Ooh, what's the donut? You will need some engineering. You take a toothpick, you stab the donut from the side, you take another toothpick from the side, and then those two toothpicks will intersect at the center of mass, and you can rest with your finger. Now, I don't know why would you be centering donut. You can just eat the damn thing. It's much better than waste your time trying to balance it. I mean, 800 people are hungry. Do we have an issue? Nah. Over here says it's working, so I don't know. Maybe it's reclining. So, it's an Apple computer. Give me a break. Of course I'm gonna go there. Get a real computer, man. It's 21st century. All right. So now we are going to take a look at an example of balancing something that is two-dimensional. Let's find a problem. Let's see. Something nice. Quarter. Okay, this is cool. We can use. Let's do 2 examples. I want to do one that it's rectangular and one that it's polar, so you can have both worlds. So variable density planes, two-dimensional plates. Okay, so here is a good one that we will probably 43 has a trapezoid, and this trapezoid has -4, +4. This is on x-axis, and then -2, 2, +2, 2 on the y-axis, and that's that. So now we would like to center this. Let's quickly agree, and I said quickly agree, that the only thing that we have to worry about is the y-bar. This object is symmetric on y-axis, which means that the x-bar from the symmetry is at 0, right? Because there is the same amount. This is uniform disk, right? Uniform piece, right? So density is uniform everywhere. And we have the same amount of mass to the left and to the right of the y-axis. Which means that if I am to take this object and rest it on the, not on the single point xy, but rested on the on a wire, which is y, it will be perfectly balanced, because we see that it's symmetric to the left and symmetric to the right. So if I use the symmetry, I know that x bar is 0. Need y bar. Now to get y bar, I need mx and m. Okay, integral for mass. Integral for mass is the double integral of rho density function is 1, because I don't have any variable density of any kind. And then I have dA for some region R. Now we see the region R. It's the trapezoid. So we get to decide which way we want to do this. Now my hope is that you will decide to use the dy on this puppy, because if you do dx, you will have to do 3 integrals, right? Because the top of dx will switch 3 times, right? There will be one over here, and another one over there, and another one over there, right? So the 3 different dx tops will create 3 different dx integrals. So that's not efficient. So we see that we are supposed to do dx and dy to be the main. Now if you're looking at the dy, that's 0 to 2, right? Because the dy, the lowest it can go is x-axis, which is y equals 0. And the highest it can go is y equals to 2. And the inner integral will be the 2 linear lines that are on the side. Now, these lines start at -4, go to -2, so they will intersect through the x-axis, through the y-axis at +4. So it's easy to actually see that those two lines have a formula of the one on the left is having a positive slope. So the positive slope of positive slope of 1, because you go 2 up, 2 over, 2 up, 2 over. So that's just x plus 4. So that's that on the left side. And on the right side, y is equal to -x. And then it's a -x plus 4. So I go right minus left, so x plus 4 on top, and -x plus 4 on the bottom. If you are not happy with the way I determine those functions, you have your algebra So go ahead, you have a negative 2, 2, you have a negative 4, 0.
The right is minus x plus 4.
Oh, wait, I have to fix them, I have to change them into y's. This is wrong. That's why I wrote them on the side, and I forgot to flip them. Yeah, minus x plus 4. I have it, minus x plus 4. Oh, that's the right one. Yeah, it goes on top. Yes, you're right. Okay, so we have to flip this because we need it to be x equals. So this is x equals y minus 4. And that is the one that goes on the bottom. And over here, x equals to 4 minus y, right? Yeah. And that goes on top, 4 minus y. Thank you. So that's our integration. Now we are going to recycle these limits and everything for the next integral for moments. So now I have integration over here. So our integral of 2, when I plug in the upper limit 4 minus y minus the lower limit, so y plus 4, I still have dx. 4's die. This is negative y, negative 2y from 0 to 2. Oh no, I have to integrate. Sheesh. That's going to be y, negative y squared, right? From 0 to 2. Why am I getting negative 4? It's 8. It's 8 minus 2y, yes. Well, good thing that someone is paying attention here. It's 8 minus 2y. I was just testing you to see if you are paying attention, and you also are not paying attention that I'm placing these dx's instead of dy's. These are all my tests, and you just keep failing them. 8y minus y squared from 0 to 2. That's going to be a 16 minus 4, and there it is, 12. A first indicator that something is wrong is when the math turns out to be negative, okay? If it was that easy to make the antimatter, I mean, we'd be out of our solar system by now. Now we have to do the mx, and mx is the same double integral. Now we have y dx dy from 0 to 2, and then the same limits. So y minus 4, 4 minus y, 0 to 2. Integral of this is yx. So y times, and x is just the stuff we have from before. So that was 8 minus 2y, if I recall, dy. 0 to 2. So that's 8y minus 2y squared dy. And now we have 4y squared minus 2/3 y cubed from 0 to 2. That's 16 minus 8, 16/3. 2 times 16, that's 32/3. So our y bar that we need to find is going to be... Now, looking at the picture, clearly, since this is on top is 2, and this is 0, right? Clearly, answer has to be between 0 to 2, right? It has to be somewhere on the y-axis, 0 to 2. Now, are you expecting it to be between 0 to 1, or at 1, or from 1 to 2? Between 0 and 1. So that's the common sense part over here. There's just more stuff, right? More weight, more mass. below 1. This is wider and bigger than the top part. So there is more mass here. So if my center is at 1, this part is heavier, it's gonna rotate and flip that way. So the center of mass better be somewhere here. You know, 0.7, 0.8, 0.9, right? Somewhere there, so that it can balance the whole thing. So now we are going to divide our 32 over 3 by 12 and get 32 divided by 36, okay. So what is this? 8 nines. So what do we get when you divide 8 by 9? Do you get 0.8 repeating? .889. Exactly as we have foreseen, right? So what is the center of mass? It is 0, 0.889. The last part for the 2D, we are going to take a look at the, let's go the quarter circle. To find the center of mass of a quarter circle. So a quarter circle, it's problem 46. So you take a quarter circle, that's the quarter circle. And you want to balance the quarter circle. Now, what are the specs of this region R? Well, region R, such that the R theta is given by R is between 0 and 2, and theta is between 0 and pi over 2 to get quarter circle. So this is where the 0 is, where the pi over 2 is, this is where the 0 is, and this is where 2 is as the radius. So now, again, we don't have any, it's going to be uniform density, so a rho is going to be 1. Now this rho also needs to be in polar coordinates. If you have a rho in rectangular and the integral is in polar, you have to convert. So now our mass integral is the integral of 1 r, the theta, 0 to pi over 2, 0 to 2. That's that. Integrate r, you get r squared over 2 from 0 to 2 d theta, and then integral 0 to pi over 2. Integral 0 to pi over 2 is 4, so it's 2 d theta, so the whole thing is pi. So the mass is pi. Right, when you integrate, you will get 2 theta, you plug in pi over 2 times 2 is, and then minus 0. Now this is interesting. We have to find the moments on the other ones, right? Now, mx was the double integral over region R, y times rho. dA. So this is going to be a double integral. Y is what in polar coordinates? R sine theta. And then you have R dr d theta. And then you have the same limits. So the first integral 0 to pi over 2. R squared integrated is R cubed over 3 sine theta. Or this is computed from 0 to 2. D theta. 0 to pi over 2. That's 8/3 sine theta d theta, which is, and now when you integrate this one, you get negative 8/3 cosine of theta from 0 to pi over 2. Now, before you freak out, cosine of pi over 2 is 0, so that's 0 minus, and then a minus is a plus 8/3 cosine of 0, which is 1. So the whole thing is 8/3. You have to do the same thing for my. So double integral of x rho dA 0, 0, pi over 2, and 2. So now this is going to be the double integral of r cosine theta r dr d theta. Same limits. Zero to pi over 2. Again, r cubed over 3 cosine theta d theta. Computed from 0 to 2, so it's again 8/3. You can kick that in front of the integral if you want. Actually, you know what? You can just integrate. One step at a time. So 8/3 cosine theta d theta. That's 8/3 integral of cosine is, very good, from 0 to pi over 2. So we also get 8/3 on this one. Now, it makes sense to have both coordinates be at the same value, because the center of mass for something that is radially symmetric like this must be on the y equal x line, right? Which is a 45-degree line. Just look at your shape, right? This shape must be symmetric on the 45-degree line. Now we see more fat on one side, so we are expecting the point to be closer to the pizza crust than to the heart. All right? So we should expect those things as engineers, right? And the reason is it's uniform density. So the mass distribution is equal, right? If this was a pizza slice, generally crust over here, right, depending on where you buy, right, it's maybe filled with cheese and stuff like that, maybe really thick, right, so heavy there. Or it might be, right, a very thin, pretty much non-existent pizza slice, but then you have mushroom and stuff over here, makes it heavier. What would that mess with? It would mess with the density rho function, which would be integrated. Now we used 1. So we are expecting uniform mushroom density. You guys you like mushroom? Good. No? More for me? It's okay. It's fine. So x bar is the same as y bar, and it's going to be 8/3 divided by the mass, which is pi. So the whole thing is 8/3 pi. So the center of mass is 8/3 pi, comma 8/3 pi. And that's that. Now, since I want to talk about regions, transforming regions for 13.7, to at least start so that we can actually finish it next class, I am going to write the formulas for 3D and quit. But the 3D stuff, it's going to be the same thing. We have integral for the mass, which is the triple integral over region D, for the density function rho x, y, z in some volume environment. So now what do you have? You have a rectangular one, dx, dy, dz, or whatever order. Then you have the general one, which has, again, dx, dy, dz with functions in the limits. And then you have cylindrical ones, and you have spherical ones. So 4 flavors over here. Now, you find the moment of yz by using x times rho. So we are going to have a moment of yz as the triple integral x rho xyz dv over region D, which will give you your x bar as myz over m. And the moment of xz is the triple integral y rho xyz dv for y bar of mxz over m. And finally myz, no, mxy is the triple integral d z times rho xy, no coughing, z dv, which is z bar mxy over m. I hope you see symmetry to these equations, and I hope you see that yzx, the rest is the same as mass, xz and then y, the rest is the same, and then xy and then z, right? Now, whatever is here, the guys are there. And also when in the future someone tells you, what do you know? Just to write this down on a napkin during, let's say, Thanksgiving dinner, you're good to go. What happened?
She said, can you imagine?
Well, I don't have to imagine, I've done it. It produces wonderful results. People that you don't want around you, they don't talk to you anymore. You just need to do it once. Right? Put certain things in perspective. So now, the situation will tell you whether it's spherical integral, cylindrical integral, rectangular integral, which again determines the string, right? R dz dr d theta, or for cylindrical, or spherical rho squared sine phi, d rho d phi d theta, and so on. And if you can exploit symmetry, do it, because the symmetry will help. But you also have to be careful, right? Because if the symmetry is ruined in any way, then you have to compute from scratch. So we're going to take a short break, and when we come back, let's transform some regions. I know it's going to be very exciting.